Okay, welcome to the fourth session of the Generalized Linear Models lecture, and here we're going to look at a more complex approach to the generalized estimated equations. We're going to do this by simply adding more moments. So at first we were looking at the first moments of y minus the mean across the t means of the t random variables of the outcome variables of interest. And here we're going to look at the second order moments as well, which is to say if we take the moments associated with the variances and covariances, and here I'm going to create a vector of these moments. I'm going to vectorize that. So I'm going to take essentially all the non-redundant moments and place them in a vector. So SI is going to have one element on each of variances and covariances rather than a variance-covariance matrix, which of course has the variances on the diagonal and the covariances on the off-diagonal. I'm just going to convert it over here, in which I'm going to use just the diagonal and the below diagonal elements, or the diagonal and the above diagonal elements. But I'm not going to put in both the top and the bottom cross diagonal because, of course, they're the same. So these are vectorizing the non-redundant moments. So our estimating equations, if we just think of it in terms of the basic generalized method of moments approach, is that we now have this huge vector of moments stacking our first moments on the vector of all the second moments, transposed times the variance covariance matrix of all of these moments inversed times this vector again. So our classic quadratic being solved, minimized in order to get our estimates now of the coefficients or parameters in the mean function and the parameters typically assumed to be in the variance function. Variance covariance matrix. So we take the derivative of the function up here, and we get a negative 2, which just goes away because it's being set to 0, but the negative 2, the summation of the first derivatives, derivative of the mean functions with respect to beta, derivative of the mean function with respect to alpha, derivative of the variance functions, covariance functions with respect to the betas, which is, again, in the originally in the mean functions, and the derivative of the variance covariance functions with respect to alpha, times this matrix of variance covariance matrix inverse, times our vector of moments. We're going to set that equal to 0. So this is the equation that we've had in the generalized method of moments framework here in the last lectures. Now, if it's the case that the betas and alphas, the parameters of the means and the parameters of the variance covariances are not related to each other, they are just separate parameter vectors, and then the derivative of the mu with respect to alpha is 0 because it doesn't contain an alpha, and similarly the derivative with respect to sigma of beta is also 0 because it doesn't contain betas, which basically means up here, let me get rid of some of this. So that's equal to 0, and that is equal to 0. And then if the covariance between y's and their s's are also equal to 0, we get 0 and 0. And really what we get then, if we were to solve these equations with all those zeros in it, is we just get the original generalized estimating equations. We would have estimating equations for mu and separate estimating equations for the variance covariances. Not actually, not technically working together, so to speak, to solve for the parameters. If, however, they are not independent that way, and these derivatives are not equal to 0, covariances are not equal to 0, then we use essentially this above set of equations. In other words, we use exactly this. If they're not equal to 0, then we are going to use, get rid of the negative 2, set equal to 0, and these are the estimating equations that we're going to solve, right, in order to get our arguments that minimize that function, which is our betas and alphas. So it's really just a generalized method of moments approach. This, however, requires not only the correct specification of the well, likelihood function in the classic sense, but of the mean function in the more general quasi-likelihood approach. But it also now requires a correct correlation matrix as well. So it's a little bit more burden on what we require to make this work, whereas before you really just needed the first. So you need to now get correct second moments specified as well. And that's a bit of a trade-off that may or may not be worth it. You can look in the literature. There's some arguments as to when GE2 is appropriate, and some would argue that because of this extra burden, it's often not necessarily a good approach to take. Okay, now let's look at this problem a little bit differently. We'll look at it from the question of looking at population models versus subject or mixed models. So population model is a model, let's say, for example, where we would say some outcomes YIT has expected values of e to the x beta. This is my linear combination, and some residual expected value, residual is equal to 0, so the expected value, again, of y given xt is e to the x beta. Okay. And what this is really doing is this is looking at a probability space, and we're just looking at the conditional probability, conditioning on the pattern of x's. And we're asking what's the expected value of y among that subpopulation, those particular individuals with the random variables x set to a certain value, right? So a certain subset or a certain group in here that we're concerning ourselves with. So this is the classic population model, right? Expected value of y given x. Take all the population, sort them by x, look at the expected value of y within each of those x categories, right? Another way is to consider the coefficients themselves as random variables. It's a latent variable type model, a random coefficient model, a random parameter model, and indeed a mixture model. So instead of my x beta, it is the x beta I, where this random variable now has a distribution. Okay. So in that sense, then the expected value of yi given x is not e to the xit beta I, but you have to integrate across the distribution of the beta i's in order to get the expected value of y given x, noting that the expected value of y given x any particular beta value would be e to the x beta I it. But when I'm not conditioned on the beta, therefore I'm integrating it out, I have to integrate across the distribution of beta. And if I want to then take that and look at the expected value at specific values of x and specific values of beta, say for example I want to look at the expected value of y given x in the mean of beta, then it would be e to the xit at that value of beta bar, if that's the one I wanted to look at. I could look at plug in different values of beta if I wanted to. I could, of course, specify a value purely, and I wouldn't even have to estimate the betas, although I would want to estimate them to evaluate whether it's an appropriate model, but assuming for some reason I knew it was the appropriate model, you can plug in a particular beta. But more importantly, you want to estimate parameters of this distribution, such as its mean, and then you could look at it at the mean. So you need an estimated beta in this case. So, subject-specific generalized estimating equations. Well, here we have the mean of the random variable is now that integral of the more general function of x betas over the distribution of beta. We consider that the variance of y given xi and beta I is going to be specified as phi times some function of the mean. This is kind of our generalized linear model approach to specifying the variances. And the variance of y given x is the variance, this is a statistical identity, the variance with respect to the distribution of beta of the expected value of y given x and beta plus the expected value given the variance of y. I'm sorry, expected value of the variance of y given x and beta. So we can look at each of these terms, right? So for A, it's the variance of the expected value of y. So we take the expected value of y given x and beta, specifying both of these, right? Subtract it from its mean. We are looking at the variance of this, so we take that minus the mean and we do it squared, right? Which is putting the 2 in there, and integrate across the distribution of the betas. That gives you the variance of the expected value. The next one is the expected value of the variance. So we take the variance, which we said was a phi times this function of the mean. So it's the phi times the function of the mean, and we take its expected value, so we integrate across the distribution of the betas. So that gives us B. So what do we have? We have an integral for the mean. We have an integral for this component of A, and we have an integral for this component B. So we can essentially plug the mean, notice the 2 together gives me this variance, the mean and the variance into our estimating equations above, and we can analyze that and use that as an estimator. And so that is a subject-specific generalized estimating equation, and it's essentially a mixture model, and it's what we've done when we did our general maximum likelihood, and we've done similar techniques, which most likely are going to include some sort of numeric calculation of the integrals, such as a Monte Carlo simulation integrals in the estimated equations, and it becomes a estimator that you can achieve by the usual either maximum likelihood or generalized method of moments, except that you're going to be plugging in ways of evaluating the integrals, which we already know. This ends this session of the lecture.